Today we're talking about molecules, covalent compounds, which some of you may have some familiarity with. Everybody's heard the word molecule. You've probably heard the word covalent, but it just refers to compounds consisting of two or more nonmetals. And by the way, let's go ahead and pause at any point here and write down what you see on the screen, and then I'll explain it. Okay, so everything ionic that we've talked about consists of a metal and a nonmetal. So if I go to the periodic table and I talk about lithium paired with chlorine to make lithium chloride, that's a metal-nonmetal combination, so that's ionic. Anything from the D block, like cobalt, paired up with nitride or nitrate or any of your polyatomic ions, still contains a metal, so it's going to be ionic. Covalent is something different. It contains only nonmetals. And it's unique from ionic, and it has to be explained differently because in covalent bonding, which is what molecules are made of, electrons are shared. So instead of them being transferred from a metal to a nonmetal, they're being shared. And the reason for that is because they can't be transferred, because to transfer an electron or two, you have to have a low enough ionization energy so that an electron can be removed. So, lithium or sodium or potassium or even one of these, group 2 or D block metals, they all have fairly low ionization energies. And if you remember what that means, it means the energy required to remove an electron. So it's easy to take an electron away from calcium or potassium or chromium or even aluminum. But if you have a pairing of nonmetals, so let's say, for example, we have oxygen bonded to sulfur, neither of them is going to be very likely to lose electrons. They both start off with 6, and they both have very high ionization energies. So you can't just take an electron from one and give to the other, or vice versa, because neither of them wants to lose their electrons very easily. So instead, what they're going to do is end up sharing. So electrons are going to be shared in a covalent compound. So a covalent bond then becomes the mutual attraction between the nuclei of two atoms that share electrons. So if I were to draw now, let's say oxygen, so sulfur and oxygen, I'm just going to draw them as little circles here. They have these positive nuclei, so each one has a positive little plus nucleus. And then the electrons that are being shared are kind of in this space right where the overlap is, and those electrons are negative, right? So negative and positive attract each other. So what ends up happening is the nucleus from this oxygen atom is very attracted to those electrons. The nucleus from the sulfur atom is very attracted to the electrons in the middle that are being shared. And so it forms a bond. It's just a mutual attraction between the two nuclei have for the same shared negative electrons. And that's what holds together a covalent bond. We'll get into Lewis structures a little bit later and actually like mapping this out and taking a look at how it works. But for right now, I just want to go into learning how to name them. So go ahead and write this stuff down and then I'll explain how it works. Okay, so these Greek prefixes have to be used to indicate the number of atoms present. So the reason I have to do that is because when we share electrons, that does not create charge. And since there's no charge, we cannot predict, just by listing the elements, we can't predict what the formula would be. So don't write this down, but as an example, lithium is a metal that's always +1. Nitride is a nonmetal that's -3 when it forms ions. And so we can predict, just by calling it lithium nitride, we already know that there's going to be 3 lithiums for every 1 nitride because of the charges. But that doesn't work when we talk about covalent compounds, because covalent compounds don't have charges. They're sharing electrons instead of transferring them. So we have to do something different. We do actually have to, with covalent compounds, indicate how many atoms of each type are present using the name. And the most common name that you guys have all heard is CO2 is carbon dioxide, right? Okay, so that di refers to the fact that we have two oxygens. Okay, now one thing I want you to notice right off the bat here, and that is that there is no mono in front of carbon. So even though there is one carbon, we don't put mono on the first element listed. So that is an important rule. Never apply mono to the first element. And that's just a convention. It's just the way that it's done. So you could have 2 or 3 or 4 all the way up to 10 on that first element, but you just don't put mono on the first element. So let's try another one. Let's say we have P2S3. Okay, so that's going to be phosphorus. Pardon me. Diphosphorus. Made a mistake right out of the gate there. Trisulfide. So we do put a prefix on the first element as long as it's not mono. We just don't put mono in the first one. And we always put a prefix on the second one. So diphosphorus trisulfide. And then we also have to give it an "ide" ending. I didn't mention that on the first one, but we always, just like with ionic compounds, we always give an "ide" ending if the element just comes from the periodic table. In other words, if it's not a polyatomic ion. So that'll happen here too. So carbon dioxide, diphosphorus trisulfide. Okay, so let's try another one. Let's go with C2H6. Okay, so that one should be dicarbon. Notice I'm not changing the ending of the first element. I'm just adding the prefix because there's 2 of them. Hexahydride. And you are responsible for knowing or memorizing those first 10, although I think probably a lot of you guys already know a lot of them, like octa means 8, mono means 1, etc. Tri means 3. So dicarbon hexahydride. Okay, so let me try maybe one more practice. We'll go the other way. Let's say we have nitrogen trichloride. What would that be? Okay. NCl3. Notice we don't start with mono. Okay. And it is, I just want to make a note here, it is very important that once we learn these prefixes, a lot of students want to apply them all the time to all compounds, but it only works for covalent compounds, so between 2 nonmetals. So again, when I go back to Li3N, it's very important that you don't start getting in the habit of calling this trilithium mononitride. Okay? That's not what this would be called. This is just called lithium nitride because it's ionic, and we know it's ionic because it contains a metal. All of these examples I just gave you, nonmetal, 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 nonmetal. Okay? So if there's a metal involved, it's ionic. And if it's ionic, no prefixes. And the reason for that is, if I just say lithium nitride, that works because that tells me that it's Li3N because lithium is +1 and nitride is -3. So I can figure out the formula from just saying lithium nitride. If I were to just say carbon oxide, that wouldn't work because, as most of you guys already know, we have carbon dioxide, but we also have carbon monoxide, one carbon and one oxygen. So because it's not dictated by charges, we can have lots of different combinations of carbon and oxygen, phosphorus and sulfur, carbon and hydrogen. So we can't just say carbon oxide. That's the reason that we use prefixes with covalent compounds.